Good morning, everyone, and welcome back to Computer Systems. Today we're going to be starting to work towards the last major topic, for assignments at least, for this semester, and that is file systems. Before we can actually get started on file systems, there's some background stuff that I want to cover. And for that background stuff, today I want to get started with the first piece of that background information, which is figuring out how the hardware works that allows us to actually store persistent data in our computers. And specifically, the story that we need to tell in order to figure out how file systems work is the story about how hard disks work. We don't actually use hard disks that much in desktop or laptop computers anymore, because solid-state drives are mostly just better. But all of the software for the last 50 years has been built assuming hard drives, and the solid-state drives that we use spend all their time pretending to be hard drives. They emulate hard drives. Though that's getting less true with NVMe devices now. But still, knowing how hard drives work is important to understanding why the software works the way it does. So that's what we're going to be talking about. So a hard drive is a device that stores data in a computer persistently. And when I say persistently in this case, I mean that if you turn the computer off and then turn it back on, your data is still there on the hard drive. Hard drives are mechanical devices that store data magnetically. And they store data magnetically on circular platters. So we have a circular platter. And that circular platter is an awful lot like a record that you would put on an old-style record player. So there's a spindle in the center that this thing's going to be the axle around which this object is going to spin. And then we're going to separate the space around that spindle into a variety of tracks. So we've got these concentric circles, and I guess for the purpose of this illustration, it's going to be between the circles is where we store the data. And in order to manage the data, we talk about the space here between these circles, the space in the tracks, being broken up into separate blocks. So we're going to store data in blocks. And it's pretty clear that, let me not start in the center, it's pretty clear that we can store less blocks on the inner tracks and more blocks as we move out, just because the inner tracks cover less surface area on the physical surface here than the outer tracks do. As we get towards the edge of the disk, the surface area of each concentric circle here is going to be larger. Now, on historical disks, I guess there's one more piece to this story, and that is that on sort of any reasonably modern hard disk, we can actually have multiple of these platters. So that makes the picture kind of confusing, but if we think about turning it this way, we would see a cylinder, except it would be broken up into, we have our spindle here, and then we've got several platters that are stacked on top of each other. And the way we actually access data on here is with this I/O arm. We have this arm which can rotate. It goes like this. So it can point at any of the tracks. But when we're talking about looking at it from the side, and we have all of these platters on the spindle, this access arm is actually a sort of giant fork, where it's going to be able to read from all of the different platters simultaneously. And on historical computers, when we wanted to address data on the disk, we'd give it a postal address style address that we're looking for. So we'd say something like platter 3, track 7, then we'd have sectors, and then block 2. Sectors are just sort of pizza slices. They totally don't make sense in the way that we'd think about doing this if we were designing this at the moment, I don't think. But that's how it worked historically. But pretty quickly, people realized that we wanted a sort of simpler picture of what's going on here. So they got rid of this addressing for blocks on the disk and replaced it with this idea called logical block addressing. And the idea is the block address on a disk is just going to be a single number from 0 to whatever, and it's going to be up to the firmware of the disk to map that single number into this like platter, track, sector, block addressing scheme that the disk cares about itself, but the computer doesn't care about. So we end up with our disk. We're going to have our we have a single platter of our disk. We have our spindle, and then we'll have like, I don't know, 3 tracks. And so this is going to be numbered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. And so that's how we deal with numbering blocks on hard drives that are as modern as to be from like 1992. 1993 is when they moved to this logical block addressing idea. And if we look at what the block numbers are going to be on the next platter, we're going to end up with the last block on this platter being like 25. And so then the first block on the second platter will be logical block number 26. That's the firmware can figure out how to do that number to location mapping. But we still have to deal with the fact that this is a physical object, so it's going to be rotating, and probably it will be rotating counterclockwise, just because that's plus angle in math. And then we have this read head that's going to come in here, and this can rotate and go back and forth this way. So this means that if we want to request that we read or write from some specific block, we have to wait for 2 things to happen. First, we have to wait for this arm to physically move into the right location, and that's the process that we call seeking on a hard disk. And then once we've gotten to the location, say we want to read from block number 11, we'll move the arm up so that we're pointing at the correct track, but then we have to still wait for the 11 to rotate all the way around and get under the read head here. The read head is going to be sort of that location there at the end of this read arm. So every time we want to do reads or writes, we have to wait for both of those things to happen. These are both latency that we have to wait for before we can do an I/O operation. And so we have our seek latency, and that's going to take, depending on how far the arm needs to move, it can take a variable amount of time. If we don't have to move the arm, it's going to take 0 time, but if we have to move like 1 track, it's going to be quicker than if we have to move from the inner track all the way to the outer track. So I'm going to say that seek time takes like 1 to 10 milliseconds. We could even be more generous and say that it takes 0 to 10 milliseconds, because sometimes it's free because we're already on the right track. The other thing is rotational latency. And again, that could take from 0 to the amount of time it takes for it to rotate completely around. And we have to then try to figure out how long does it take for it to rotate completely around. And a normal hard disk for like a desktop computer or a laptop computer where you bought an expensive fast hard disk that uses extra power, we're talking something like 7,200 revolutions per minute. And if I were doing this as a live class, I'd have someone do out the math to try to figure out what that means. I'm going to skip the arithmetic right now because I'll definitely take 10 minutes and get it wrong, even though it's trivial. But if we take 7,200 RPM and figure out how long it takes to do 1 rotation, it turns out that we're going to end up with something on the order of 8 milliseconds to do 1 rotation. And that means that our rotational latency is going to be, on average, like 4 milliseconds. And now if we look at this a little bit and stare at it and round a bit, we see that sort of on average seek latency is going to take 5 milliseconds. On average rotational latency is going to take like 5 milliseconds. So our average total latency is like 10 milliseconds. So every time we want to do a single block read or write to this disk, if we aren't already in the right location rotationally and arm moving, we're going to have to spend 10 milliseconds waiting for the read-write head to be in the right place physically. Mechanically, we have to wait that long. There's one other consideration that we have to think about in terms of how long it's going to take to do I/O with a hard drive, and that is our sort of sequential read or write speed. And that is, on a reasonable mechanical hard drive, maybe 150 megabytes per second. Now, 150 megabytes per second is kind of slow compared to what an SSD will do. This hasn't even really changed in the past 15 years. That's what the number would have been in 2002. That's what the number is now. Maybe you can get one that goes 200 now. Maybe it would have been expensive to get one that went 150 then. But it's not like most of the other components of computers where this is drastically improved. And that's one of the important things here with a hard disk, is that when we're doing sequential reads, we don't actually have to wait for anything. If we want to read block 0, then 1, then 2, then 3, then 4, we point the head at 0, which is going to take us 10 milliseconds to seek, and then we just wait for the thing to spin, and just with the thing spinning under us, as we read one block, we'll move on to the next block, and we'll get to read the next block that we want, and there's no seek latency during a sequential read or write. There's no rotational latency really either. That rotational latency is built into the read speed that we're looking at. So what that means is that if we want to do a sequential read of 150 megabytes, our disk reads at 150 megabytes per second, so it's going to take 1 second. The other case is what happens if we want to do a sequential read, if we want to do a random read of 150 megabytes. And that raises the next question, which is how big is one of these disk blocks? And so traditionally on hard drives, disk blocks were 512 bytes. On modern disks, you'll frequently see disk blocks be 4K, because that's the page size on modern operating systems with modern CPUs, pretty much all of them at this point. And so you'll frequently see 4K disk blocks just because that makes sense in software. But for this example, we're going to take 4K because it's the easier number. So if we want to do 150 megabytes, and we want to figure out how many 4K blocks that is, 150 divided by 4 is going to be like 33, and megabyte divided by kilobyte is going to be 1,000. So we have like 30,000 disk blocks here. Now, 30,000 disk blocks randomly scattered around the disk, that means we're going to have to do 33,000 seeks. Every seek is going to take on average 10 milliseconds, so we're looking at 33,000 times 10 milliseconds. So that's 330,000 milliseconds, which is 330 seconds, which is like 5 minutes. So for random reads or random writes, doing 150 megabytes of data takes 5 minutes. For sequential read or writes, doing 150 megabytes of data takes 1 second. And that gives us sort of the key idea of this whole story, which is that if we want to optimize to be efficient on hard disk drives, it's real simple. All we have to do is do sequential read and write and not do random read and write. And the harder we try to accomplish that, the better our performance is going to be. As we go through file systems, we'll discover that people really didn't go to that crazy an extent to actually accomplish this, and this is why a lot of computer systems are slower than they've needed to be. We have ways to get a lot of sequential I/O and less random I/O, but as anybody who remembers using Windows from years ago will recall, defragmenting is a thing, and that again is trying to help the system avoid this random I/O, which is super slow on hard disks. All right, I'll be back in a second to talk about a little bit more modern stuff, solid-state drives.